And start. All right. Welcome to the DDPS seminar, everyone. Let's go over some logistics. First, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me introduce our speaker today. It is an honor to host Jess Capecelatro, who is an assistant professor in the Department of Mechanical Engineering and Aerospace Engineering at the University of Michigan. His research group develops numerical methods and data-driven approaches for the prediction and optimization of messy turbulent flows relevant to energy and the environment, often multiphase and reacting. Prior to joining Michigan in 2016, Dr. Capecelatro was a research scientist at the Center for Exascale Simulation of Plasma-Coupled Combustion at the University of Illinois. He received a bachelor's in science from SUNY Binghamton in 2009, a master in science from the University of Colorado Boulder in 2011, and PhD from Cornell in 2014. He is a recipient of the National Science Foundation Career Award, Office of Naval Research Young Investigator Award, and the ASME Pi Tau Sigma Gold Medal Award. All right, today, Dr. Capecelatro will present an interesting topic, which is turbulent disperse two-phase flows, simulations, and data-driven modeling. Please enjoy and expect a wonderful talk. Now, without further ado, let me pass the baton by asking one random question as usual. Today's random question is, what is your favorite sports team if you have any? It's a question for you, Jess.
Okay. I grew up in New York, and I watched a lot of professional football, and so New York Giants fan. But yeah, most of the sports I do now is rock climbing, ultimate frisbee, and there's not a lot of professional teams. So yeah, I don't follow much sports anymore. But used to be a Giants fan.
Thank you, Jess. It's all yours.
Okay, thanks. So it's really an honor to be here. This seminar series has been I've attended a couple of them, and the lineup of speakers have been really fantastic. So it's been a silver lining of this pandemic to be able to watch and see these the seminars in this series. So the talk today is going to be on dispersed two-phase flows, namely gas solid or gas particle flows. And I like this image here. This is from our collaborator, Vahid, who was at Iowa State, worked with Shankar Subramaniam, and we work closely with now, looking at a direct numerical simulation through a suspension of particles. And I like to show this on the title slide because it's just a good image to have in your mind when we talk about these types of flows where particles have an order one effect on the background turbulence. And so you can see here that there's deflection of the streamlines, there's wakes shed past the particles, and that's going to have an order one effect on the background flow. And those are the types of flows we'll be talking about today. So as was mentioned, our group, we tend to we're a computational group here at Michigan. I think everything we do is under the umbrella of turbulence. We do turbulent combustion. I have a student looking at adjoint-based optimization, which I know there might be folks in the audience here interested in that. But the talk today is focused on some of the multiphase turbulence modeling that work we've been doing the past couple years. But probably my biggest focus now is on compressible gas particle flows, which I'm not presenting today, but it's a very, I think, exciting area of research. There's been a lot of developments these past even just 1 to 2 years. So I'm currently working on a review article on compressible gas particle flows on the modeling aspects. So I think it's a very exciting area, and happy to talk about that offline. The work I'm presenting today is funded by NSF, and I'm mostly presenting work by my postdoc, Aaron Latanzi. on some of the stochastic modeling he's been doing for drag. And Sarah, who's in the audience here, who is a former, she just defended her PhD and is a new faculty member at Oakland University in Michigan. And so most of the stuff on the multiphase turbulence modeling is her work. And this has been research we've done in collaboration with Shankar Subramaniam, his student Vahid, who's now at Florida State, and Rodney Fox. So turbulent dispersed two-phase flows are, ubiquitous. There are many different applications. Here I'm just highlighting a couple simulations that we've done in the past couple of years. So some of the types of flows we're interested in, just to give sort of an idea of the type of physics that's present in the vast range of applications. So this is from expiratory flows, obviously related to COVID-19. A lot of the flows we're talking about today is motivated by conversion of catalytic particles, aiding the conversion of fuel to useful, feedstock to useful fuels. So one example is biomass pyrolysis. But a lot of our work has been with NASA, who's interested in plume surface interaction. So this is a Euler-Lagrange simulation of an underexpanded jet on a bed of particles. And there's a lot of challenges with these types of simulations. We've been doing a lot of modeling and method development for in the compressible regime. So the talk today, we want to look at turbulence modeling of what I call strongly coupled flows. And so as an example, I want to distinguish this with the more classically studied particle-laden flow in the dilute limit. And so what I'm showing here on the left is a classic example where you have a heavy inertial particle, solid particle, in a turbulent flow where the volume fraction, epsilon p, is very small. The density ratio is very high. So think, gas solid, order of 1,000, 2,000. But in this case, the particle diameter is smaller than the smallest scales of turbulence. And there's a lot known that you get preferential concentration. You have enhanced settling as particles preferentially sample certain size regions of the turbulence or the eddies. And there's a lot of really nice work on that regime. The flow regime we're interested in today is we're still looking at gas solid, so large density ratio, but now we're looking at finite volume fraction. So for example, this image on the right is a experiment done at the National Energy Technology Lab, the DOE lab. And I think this was at about 1 or 5% concentration on average. And so here, the volume fractions we're talking about are going to vary between 1 and 10%. And the particle Reynolds number, the Reynolds number based on the particle diameter, can be order of 10. And you can see that there's a lot of interesting dynamics. You get these large scale clusters that form. And unlike in the dilute limit on the left, here the particles really have a large effect on the background flow. And that introduces a lot of challenges for turbulence modeling. So the next 3 slides I shamelessly stole from Sarah's PhD thesis, but the main idea here is that the challenge is really that the classic energy cascade that we'd see in single phase flow sort of breaks down, because now the particles will induce wakes at the small scales, or if they assemble into clusters, they can induce very large scale wakes that introduces energy at the small scale that can then cascade back up. And so that's one place where the classical theories of turbulence starts to break down, when we have these denser suspensions. So there's a nice history of the development of turbulence modeling, starting from the sort of the turn of the 20th century, the so-called Buznesk approximation, and the eddy viscosity model. I'm sure many people here are familiar with this. Kolmogorov hypothesis, so the energy cascade, and using that in the context of large eddy simulation has been very successful. In the 1970s, the development of tensor basis, and so an invariant basis sets were developed, and which is required for RANS modeling. And the latter half of this talk is going to be focused on multiphase RANS modeling, so we're going to really make use of this. And the so-called K epsilon model, which is really the workhorse today in a lot of sectors. But what we see is there's been a lull over some time, and then in the 2000s, and really, as everyone's aware, the last just couple of years, data-driven modeling has exploded, right? And so this has taken forms of closure modeling, uncertainty quantification, model augmentation, and most often in the context of neural networks. The approach we take is going to be an alternative to neural networks, and I'll explain that a little later. Compared to single-phase turbulence modeling, multi-phase turbulence modeling is really seen, it really lags the development. So starting really in the 1980s, there's been a lot of models proposed based on, or at least multi-phase RANS models proposed that were largely derived from extensions of single-phase turbulence. And in 2014, our collaborator Rodney Fox derived rigorously the Reynolds average two fluid equations, and I'll show sort of that process a little later. But this leads to a very large number of unclosed terms that a simple augmentation of a single-phase model just won't work because they're in terms of drag and volume fraction that just don't exist in single-phase flows. So today's talk, I've broken it up into two parts. The first part is on some new developments in our group on modeling and simulation. So this is specifically focused on a new stochastic drag force to capture some of the detailed physics at the microscale. And then the latter half is going to use that modeling sort of framework, which we'll call it's an intermediate step between the DNS and RANS, using data from these simulations in order to develop multi-phase RANS models. Okay, so a couple of preliminaries. The way I've decided to frame this talk was instead of doing a deep dive and really talk in detail about the way we do the data-driven modeling, I thought it might be more interesting, or at least helpful, to really talk about some of the physics first and motivate why these data-driven approaches are show promise and are needed compared to more classical approaches. And so it won't be till towards the end that we'll actually talk about some of the more machine learning type of stuff. But that's the data-driven aspect will definitely be relevant throughout. So to begin, for this talk, the flows we're interested in, we have solid particles we'll assume are rigid and spherical in an incompressible flow. So the nice thing is that we know those equations, the Navier-Stokes equations with appropriate boundary conditions at the surface of each particle. It describes these systems well. I have an asterisk here because when you have melting or devolarization, other phase change aspects, this is challenging, but at least for isothermal or inert particles, the equations are known. And you can see that the fluid force on the particle shows up through this fluid stress tensor integrated at the surface of the particle, which obviously requires subparticle scale resolution. So if we wanted to do a DNS, we would need to implement some type of Seymour's boundary method that I'm showing here with a resolution smaller than the particle. And when I initially created these slides, the state of the art at the time was order 10 to the 3. There's been some recent papers looking at larger scale simulations, so more particles that are fully resolved, though typically sacrificing the number of grid points across the diameter. And so it's still very challenging to get more than 1,000 fully resolved particles. So the alternative approach, whatever modeling approach we decide to take, inevitably will require some type of averaging, right? So we have to solve an average set of equations to be able to simulate larger scales, which inevitably leads to unresolved or subgrid scale terms that need to be modeled. And so sort of the idea here is that fluid stress tensor, right? So this is comprised of pressure and viscous stress. We can think of applying an average or a filter to it. That's what I'm showing in this tau bar. And that averaging operation has a length scale that's larger than the particle. And so we can pull it outside this integral. And so this represents fluid forces acting on the particle based on the larger resolved scale. And then we have everything left over. And it's not difficult to show everything left over, i.e. the fluid stresses at the particle scale is essentially the drag force. And so in order to close the system of equations, or at least this equation here, we need to introduce a model for this unresolved fluid stress along the surface of the particle. And classic closure is that from George Stokes, who proposed in the limit of small Reynolds number an isolated particle. We have a model Stokes drag that's shown here. Now, obviously, if we have a accelerating either reference frame or accelerating particles, or there's non-uniform flow effects, additional terms appear besides just Stokes drag. And so what I'm showing here is the so-called BBO equations. So particles might exhibit an added mass force, specifically for lower density ratio or bubbly flows. A Basset history term. This is really due to delayed boundary layer development. Again, it's usually small for gas solid. And then the so-called quasi-steady drag force, which is where Stokes drag would appear. But for these denser suspensions, when we have neighbor effects, right? One particle's wake might interact with another particle's wake. We get volume fraction effects or finite Reynolds number effects. You can't readily apply such an equation. And so the idea then is, again, we have this Newton's second law, this ODE for the particle position. It feels a resolved stress. This is sometimes referred to as the undisturbed force or the pressure gradient force. And then this FD is everything left over, which is usually closed with correlations from either experiments or simulations. And so in the last probably 10, 20 years, or yeah, I guess some of the first DNS simulations about 20 years ago, several models have been developed. The idea is you have a box of particles, you fully resolve it, you apply a mean pressure gradient, and then you, in these simulations, the drag is an output. And then you run a bunch of simulations, you come up with correlations. And so one popular drag model is by Tinetti, Garg, and Subramaniam from 2011, where you have a drag force over, this represents the average drag force in that suspension, and it's correlated based on the mean Reynolds number and the volume fraction. And this is really commonly applied in most modern codes. I mean, the idea of applying a drag correlation to particles is standard practice. Every commercial software with particles does this. Now, some of the challenges, though, is that when you go to larger scales, or when you have some of these complex flows or high Reynolds number flows, this drag correlation really represents the mean. But there could be significant deviation about that mean. And at very large scales, you can have clustering and heterogeneity existing that such drag correlations just can't capture. And work out of Anthony Wax's group, along with Balish and Dar's group from Florida, have published a number of papers where they show that the variation about that mean is quite large. And so what this is showing is if we have a suspension of particles, you look at a PDF of the drag force, the existing correlations work pretty well to capture the mean, but the standard deviation can be just as large as the mean, which is clearly not accounted for in existing models. And using existing drag laws tends to fail, at least it's difficult to capture some important statistics like the particle velocity variance or the dispersion. And the main idea is if you can imagine having three scenarios. So here I have a grid cell. Each grid cell has the same Reynolds number, right? I have the same mean velocity and particle velocity and the same volume fraction. Each one has 4 particles. But this particle in green should experience a significantly different drag force depending on the orientation of its neighbors. But using standard drag correlations would predict that these particles all have the same drag force. So that's where the issue comes from. Now there's been, over the last 5 years, I'd say, a lot of focus on how to improve these drag laws. There's been some nice work from Balash and Dar trying to do this deterministically, where you loop through neighboring particles and try to map or superimpose the effective neighbors on that particle of interest. But we've decided to take a different route. The main idea here is that each particle will experience both the drag force on this particle I will have a contribution from sort of the mean drag. That's where an existing drag correlation would give, plus what's left over, and that would be given by some distribution. And it turns out that previous simulations have shown that PDF tends to be Gaussian, which is convenient. And so the way we're modeling the variation in that drag force is using a Langevin equation. So applying a Langevin equation to the force results in Ornstein-Uhlenbeck process. And here we could see the incremental change in the drag force has these two terms here, which requires closure. This tau f is an integral timescale of the fluid force fluctuations. And the sigma f represents the standard deviation. And here W is a Wiener process, or essentially a Gaussian white noise. And work we've been doing from extracting these statistics from DNS shows that this is a good approximation of what's going on, because the drag force is indeed Gaussian, and the autocorrelation in the force fluctuations is indeed exponential. And so treating this force as a Langevin equation should be promising and allow us to capture important statistics. A side note is we treat it's a lot more common to treat the velocity statistically. So this usually in most fluent or open foam, these so-called random walk models tries to plug in the fluid velocity that's not known as a stochastic variable. What we're finding is if you treat the force stochastically instead of the velocity, you can guarantee certain statistics, but more than that, it results in the velocity to be Markovian process, which means that there's promise of doing such an approach to capture history effects like added mass. And so one thing we're interested in now is looking at stochastic added mass. But this is sort of how it works. Our particle will feel forces due to collisions, maybe gravity, the resolved stress, so that's the pressure gradient force, and then what's left over. What's left over is going to be the mean drag, which we can model with existing correlations, and then the fluctuating part. The mean drag, we already have correlations, so that's good. The fluctuating part is described with this OU process. We have found in our previous work that time scale is reasonably predicted using the time between successive collisions, and from kinetic theory, we have a model for that. This is based on the granular temperature and the radial distribution function, and so we readily have a model for this term, but we need a model for the standard deviation. And looking at particle resolved simulations, it turns out we can get a nice collapse across volume fraction and across Reynolds numbers if we normalize the standard deviation with the drag force for an isolated particle. And so now we have a closed form expression for all of the terms in that model. And briefly, we just want to see, well, how well does it work and how does it compare against existing methods? So what we do is we're looking at two canonical systems. So the so-called homogeneous cooling and homogeneous heating case. So imagine you have a box of particles, there's no walls, and you force a flow through there. If the particles are at rest, eventually its granular temperature or the velocity variance of the particles will increase and reach some steady value. So that's the heating case. Alternatively, if the particles start with some finite variance, some finite velocity fluctuations, it'll cool to some steady state. And what we're showing here is that granular temperature or velocity variance normalized gives us a Reynolds number based on the granular temperature as a function of time. The symbols are data from DNS. Now, just a side note, if you recall, the closure we used, one was based on kinetic theory for the time between successive collisions, and one was based on the standard deviation of the force, which was taken from fixed particle assemblies. So, and we're comparing this model to DNS of freely evolving particles. And so this is very much not an exercise of tuning any parameters. It's a true prediction. And what we see is the red is the Euler-Lagrange method with the Langevin force, the stochastic force. And we see we both capture the transient behavior in addition to the steady state, whereas the blue is showing the standard approach where you only have the mean force, which is unable to capture those fluctuations. And similarly, across Reynolds numbers and volume fractions, this is the heating case, starting with particles are immobile, you force a flow through and their velocity fluctuations increase and eventually level off. We see very good agreement. So this is just a new model that we've been developing, and it's also showing promise looking at lower density ratio suspension, so looking at bubbly flows as well. But the title of the talk was on turbulence modeling, and so what I'd like to do is now zoom out and look at some larger scale systems, right? This box of particles, we're talking about, I think, on the order of 100 particles, very small scale. But let's zoom out. And so as a representative example, this is that chemical looping reactor where I showed that image earlier from that fluidized bed. And, I just want to reiterate that this is very challenging when it comes to turbulence modeling, because at the smallest scales, you have collisions, you have wakes past particles. If there's heat transfer, you can have convection or conduction. And what happens at the small scales feeds back to the large scales in terms of clustering, and that has an order one effect on the background turbulence. And so what we're going to do is first derive a set of intermediate equations, and these are the equations we are solving in the homogeneous heating and cooling for the model. So the fluid phase, if you locally average the Navier-Stokes equations, you get a new set of equations that look very similar, except now we have a fluid volume fraction appearing. In addition to that, in the momentum equation, we have this phi is mass loading. And so this is just the relative mass of the particle to fluid phase. And then we have our interphase exchange. So this is how the fluid feels the effect of drag from the particles. So it feels both the drag force and the resolve stresses. Now, the idea here is taking those equations instead of the original Navier-Stokes equations and applying an averaging operation to that will allow us to retain more physics. And so the idea here is we're going to do the usual Reynolds averaging, but because there's volume fractions that pop up in lots of places, we're going to do so-called phase averaging. This is analogous to Favre averaging for variable density flows, but here we have volume fraction instead of density. And so we could define a residual about the mean. So a double prime is a fluctuation about the phase average fluid, and then the triple prime are fluctuations about the double prime is a fluctuation about the particle phase average, and the triple prime is based on the fluid. And you can imagine doing this to the Navier-Stokes equation is going to lead to a lot of unclosed terms. So I want to just highlight one example where we have a channel flow, meaning we have one non-homogeneous direction. That'll be the wall normal direction. And other terms will cancel out. The derivatives in the homogeneous directions cancel out. And what we end up with is a Reynolds average equation. So this should look very similar to what we'd have in single phase channel flow if we got rid of these terms in red. And so the terms in blue are unclosed terms that appear in the Reynolds stress model due to pressure redistribution, production due to mean shear, so due to mean gradients, and a dissipation rate. So this is exactly what appears for single phase turbulence. But the terms in red are new. And this is new in the sense they wouldn't exist if there were no particles. So we have a so-called drag dissipation and exchange rate. So this is how fluid turbulent kinetic energy is transferred between the phases. And you can see it's proportional to the mass loading. So in the limit of low volume fraction, this goes to 0. And then we have a drag production term. So this is an interesting term because in homogeneous flows, we have no mean gradients. You would have no production of TKE because this P shear term would be 0. But this shows that in the presence of particles through coupling from drag, you could get production of TKE even in the absence of mean shear. And this UD is based on, it's a drift velocity, so it's the mean phase difference. So in order for particles to induce turbulence in the fluid, you need two ingredients. You need finite mass loading. So particles need to have be high enough volume fraction and high enough density. And you need to have locally a non-zero mean slip velocity. So that's what drives turbulence in the particle phase. And the idea here is we want to avoid going from the microscale directly averaging the Navier-Stokes equations, because that's going to end up lumping a lot of important physics into a very small number of unclosed terms, and instead go from the microscale to inform these mesoscale equations, and then the mesoscale apply that averaging, and then use that to inform the closure for the macroscale equations. So here's just an example where we're solving. This is in our in-house code. It's a pretty vanilla finite volume second order low Mach number solver with Lagrangian particle tracking. Here we're solving those volume filtered equations. So it's the Navier-Stokes with the volume fraction and momentum exchange terms. And what we see is we have a turbulent channel flow. Reynolds number is 10,000. Density ratio is 2,000. And if we look in the case of very dilute flow, the fluid velocity resembles what we might expect for a single phase flow. And if we look at the budget of TKE, you get a balance between the shear production and viscous dissipation. Now, if you keep everything the same, but we only add more particles such that our mass loading is now order 1, here the mass loading is 2, there's enhanced dissipation through drag, through that drag exchange term, which relaminarizes the flow, and you can see the budget's completely killed off. And if we keep adding particles, and now our mass loading is 20, again, this is a 3D simulation, I'm just showing a 2D cross-section, the coupling between the phases leads to clustering, and the clustering leads to large-scale wakes, and now we see fluid TKE, but it's a very different characteristic than the single-phase turbulence. And here the budget, we have drag production balanced by drag exchange. So here, Reynolds number is constant. The only thing changing is the mass loading, and we have very different flow characteristics. Another interesting thing is if we look at the spectrum of TKE, up here is the single phase case, so the classic k to the minus 5/3. And in the dilute limit, you can see that particles are really enhancing the TKE at the largest wave numbers. So that really represents, the wakes past individual particles. But as you increase the mass loading and you get clustering, the particles have a broadband effect, and the TKE is reduced across wave numbers. Okay. The final part of this talk, I just want to talk about looking at how we develop closure models for the Reynolds average terms. And I want to focus on what I would consider the simplest possible case that's driven by coupling with the particles. So the channel case is that I just showed is a nice framework for looking at these effects of particles on the turbulence, but because of that wall normal direction, it leads to a bunch of terms. And so to simplify things, we're going to consider a homogeneous box of particles, so it's triply periodic. Particles are randomly distributed, and the fluid's initially at rest, and we have gravity. And because of gravity, particles start to settle. And here we're in the frame of reference of the fluid, so we force the mass flow rate to be 0. And due to the coupling, particles will spontaneously form these dense clusters, and we can see here the fluid velocity now. We have these high-speed vertical flow in between clusters. Meanwhile, the clusters entrain the flow downward. And so in the absence of particles, the flow would be at rest, and here the fluid TKE is entirely due to the coupling. And we're going to consider a couple different cases, so different volume fractions from 0.1% to 5%. Which corresponds to mass loading between 1 and 50. And what we want to do is evaluate those unclosed terms that appear. So that's the drag production term is one of the primary ones. And before I joined Michigan, this was work I was doing with Rodney Fox. I spent 2 summers in France on this work, and it became apparently clear that there's a large number of terms, and there's a huge dimensional space, right? So unlike in single phase flow where you really have a Reynolds number, here we have density ratio, volume fraction, a bunch of extra terms, and coming up with robust closure models has been quite challenging. And so the work that my student Sarah, former student Sarah, has been doing is is looking at using some data-driven approaches to come up with model closure. And the approach we decided to take was we wanted to have a model that ends up with a nice algebraic form. So we wanted to avoid using neural networks because we wanted to have an algebraic expression for these terms. We also wanted to make sure that it had embedded important physics, for example, form invariance. And so what this follows is essentially a sparse regression technique that I'm sure a lot of people here are familiar with. And the idea here is we take some tensorial data. So this would be data that can come from either simulations or experiments, in this case from the Euler-Lagrangian simulations. And we want to postulate a model based on these coefficients beta, which themselves can be nonlinear, but we're going to look at linear combinations of them. And we have this T here are basis tensors, which need to be formulated by the user based on knowledge of the physics. And a couple of key notes is that forming this as tall, skinny vectors ensures that the beta does not vary with orientation. So that's an important ingredient for form invariance. And by doing a linear combination of the basis functions guarantees the Gaussian invariance as well. And what we do is a sparse regression, so essentially an optimization where we have an L2 norm where we regress the data onto the model. And then we add an L1 penalty in order to induce sparsity. So this ensures instead of enslaving the data, the model to the data, it'll identify which terms are important and which terms play less of a role, which is quite useful. Now, as I said, we have these tensor bases and the user needs to decide, input them. We see this as a feature because you need to know something about the physics and as opposed to, being purely data driven. And in the context of single phase flow, if you look in, for example, Professor Stephen Pope's textbook, you can find a table of these basis tensors that exist. And we, in our physical review fluids paper, we demonstrate this method on a bunch of single phase flows and shows that it works quite well and is able to identify the algebraic models for the Reynolds stress terms using these basis tensors. But the basis tensors for multiphase flows haven't yet been developed. And so in our a recent JFM paper, Sarah derived the non-dimensional symmetric deviatoric tensors for these coupled fluid particle flows. And so they're basically a function of the relative velocity and the Reynolds stresses of each phase. And this is an example of what the simulations look like at 0.1% concentration and 5% concentration. And so if we use this data from the simulations and we look at what sparse regression gives us, this is an example of one of the terms. This is that drag production term. And we see here that we're able to come up with a compact algebraic expression based on, in this case, the mass loading and some of these tensor bases, so based on the relative velocities. And it works quite well across the volume fraction and Reynolds number. One thing we're curious about was all of this simulation data is statistically stationary. So meaning the data we provide, it's average in time. It's essentially a single point. And so what we did is we took the simulations and we reversed gravity. And so we looked at the transient behavior. And here we're looking at the mean settling velocity, the particle phase versus time. And using the Reynolds stress models from the stationary data still gives us a very reasonable prediction. And so this is quite promising. We're now using this approach for more complex systems, both on channel flows and we have a recent paper that'll appear soon online, looking at the heat transfer. So here we're looking at the effect of clustering on the thermal entrance length. And so you can imagine if you had a uniform distribution of particles and a temperature difference between the phases, you would have a smaller entrance length, meaning the distance that the fluid temperature relaxes to an equilibrium, compared to a more realistic case where we have strong clustering. And we're able to come up with new, at least correlations for that entrance length, in addition to Reynolds stress type models for the temperature. And just a final note before I wrap up here. One of the challenges with the sparse regression is that the coefficients in beta need to be input by the user. And what we're finding is that we can make use of gene expression programming sort of to automate that process. And so Sarah has an archive paper here where we combine sparse regression with gene expression programming. And the idea is we still want to end up with a compact algebraic expression. We want to leverage the properties of the sparse regression for the form invariance. But we also want to automate some of the challenging parts. And so here, what we're doing is using gene expression programming to come up with the coefficients appearing in beta in order to come up with more general expressions for the enclosed terms. A couple notes on that. Gene expression programming does not enforce the relation that the models to be linear with respect to the basis tensors. And so that's why sparse regression is important to guarantee form invariance. And preliminary results are showing that when you combine them, it's able to, it's a nice compromise with at least embedding certain physics, but also automating some of the process. And so in conclusion, we're talking here about these dispersed two-phase flows where the particle phase has a strong effect on the background turbulence. The drag force acting on dense suspension exhibits a large variation. And so treating the force stochastically is showing promise to guarantee certain statistics like particle velocity variance and dispersion. Multiphase turbulence modeling, following traditional approaches of directly averaging an average Stokes is challenging because it really lumps a lot of the physics into a small number of terms. And so instead doing this sort of sequential approach of locally averaging Navier-Stokes and then Reynolds averaging those intermediate equations allows us to retain more physics, but it results in a large number of unclosed terms that need to be modeled. And sparse regression is showing promise for developing closures for those terms. And with that, I'm happy to take any questions that anyone might have.
Thank you so much for the great talk, Jesse. We do have one question from Gavin. He was wondering about what is the gene expression programming. So
I skimmed over that for two reasons. One is it's very recent work. We have an archive paper here, but it's very much we're just starting to look into it. So gene expression programming is it's a considered an what's it called? Sorry, the word slipped on my mind. An evolutionary algorithm in the sense it's a symbolic method, and so it can work with sine functions, cosines, exponentials, and so forth, and it tries to come up with what's the best combination of all these various symbolic expressions. And there's very nice open source code online. So we basically took off the shelf open source gene expression MATLAB code to do this part. And the nice thing is, you can have options on how many terms and how complex those terms are. So without the gene expression programming, the user would have to decide what those kind of functional forms or combinations of those coefficients might look like. The gene expression programming sort of tries to determine what those expressions are, if that makes sense.
That sounds really similar to actually the work done by one of our own. I forgot his name, but he did come up with some symbolic learning algorithm.
Yeah, if you read this archive paper, Sarah goes through. There's been a couple people who've used it for turbulence modeling, and not many, but there have been a couple. And I'm sure I'm sure it's been used in other areas as well.
Yeah, I mean, it'll come back to me. So if his name comes back to me, I will forward his name so that maybe you guys can connect it. Mm-hmm. Okay. All right. I don't have any other questions from the chat room, but I have some of mine. Oh, sure. Okay. Before I go to my questions, there's another question from Chandler. Mm-hmm. He said, "Hey Jesse, I really enjoyed reading your work on stochastic drag modeling.
Okay.
Have you put any thought towards how two-point statistics between particle positions and velocities, for example, radial distribution functions, may impact your drag moments?
This is a fantastic question, and it's exactly what we're looking at right now. And so, maybe to clarify to some folks, you can imagine you have a suspension of particles that are going to evolve with the flow. And one of the arguments I've been making is some of these deterministic, if you have just two particles settling in a viscous flow, right? The particle upstream will fall in the wake of the other particle and catch up, and it's the so-called drafting, kissing, tumbling, right? So meaning if two particles near each other, they're going to be influenced by each other's wakes. A deterministic approach that directly accounts for neighboring effects should be able to capture that, and I think Balachandar has shown that. A stochastic approach that I presented here won't, right? Because we're sampling from a distribution, and so it doesn't really have knowledge on the specific pairwise interactions. But my argument's been, well, if we have millions of particles, who cares? What we care about is getting the right statistics. And that's something an argument I've posed, but at the same time, my collaborator Shankar Subramaniam has been looking at connecting this with two-point statistics, and we believe that it is possible in this sort of Langevin framework, stochastic framework, to capture the radial distribution function of the two-point statistics. And the reason why I think it's extremely exciting is because it's commonplace in industry and throughout academia to do Reynolds Average Navier Stokes, right? You do RANs for the fluid, and then you do Lagrangian particle tracking, and then you do stochastic random walk models for the particles to say my fluid has an unresolved turbulent motion. I'm going to treat it stochastically. Those methods can't capture preferential concentration. They're unable to get these pairwise interactions, and I think this might be a missing link, but it's something we're just now starting to look at, and I think it's a really exciting direction. I hope that answers your question.
I hope that answers the Chandler's questions. You're okay. He said thank you. Okay, so he's satisfied. Okay. Another question from Maxwell. He asked, is there any technical reason why radiation is neglected in the chemical looping reactor model?
Yeah, that's a good question. Because it's hard. So everything I've shown up to this point has been isothermal. And if you look at these experiments also are isothermal, but obviously the motivating example is a thermally evolving, catalytic type of reactor, right? So chemical looping reactors are operated at elevated temperature where radiation is likely important. And obviously, Stanford has been doing a lot of great work on this in recent years, mostly in the dilute limit. So here we're looking at convection, and we neglected radiation, mostly saying that clustering affects the turbulence, and that's going to affect the vective transport of the temperature. But you're absolutely right that radiation will play a role at high enough temperatures, and I think there's a lot of good work to be done in these denser suspensions. I don't know of any really good models that exist for radiative transport when you have these denser suspensions, and you can imagine it's difficult because you have a lot in terms, when you model radiation, you have to account for, you usually do Monte Carlo type of simulations, have all these angles, and here you're going to have deflections off of all the surfaces of the particles, and it becomes an n-body problem. So yeah, it's an area of research I think that's very exciting, or would be exciting. I don't know how much it's being pursued now, at least at these volume fractions.
I see. Thank you, Jesse. Okay, I don't see any question from chat room. I have a question about the scalability. You said you are tackling the larger scale problem with the particle flow. What was the largest problem you could solve?
Yeah, I didn't do a good job, I think, talking about the simulations we were running, right? So here we're doing two things. One was the stochastic modeling, and that framework is used for us to run these more canonical simulations to generate data. Now it turns out that, and then I glanced over this, when we scale up, I showed that homogeneous heating and cooling where we have an order of 100 particles, and there the stochastic model plays a big role. It turns out for this cluster-induced turbulence, most of the heterogeneity is driven by the larger scale cluster dynamics. So in that case, the stochastic modeling actually plays a little role, and the existing drag models do a pretty good job. And so the simulations we're performing to generate the data. So these homogeneous simulations, the channel flow I showed, and these heat transfer simulations are on the order of, we're tracking individual particles on the order of, I think, 30 million particles for this case. We've gone up to 500 million particles is probably the largest we've done, because our grid spacing is on the order of the particle diameter. But even at those scales, we're never going to tackle the reactor scales, and that's why we're doing the Reynolds averaging, right? And so if we look here, those 100 million particle simulations, that's to generate these mesoscale simulations to generate the data. And we're applying it to look at RANS types of frameworks that could be applied here. And that's where this is a direction I want to go, is actually start applying them in RANS solvers, right? Everything to date has been more, we've developed algebraic models, but not actually tested them at full scale. And that's an area I'm hoping to look at.
Yeah, sounds good. Thank you. We do have another questions. From Maxwell again, why is the performance of this approach for cases where the fluid and particle velocities are very close in magnitude?
Sorry, repeat that?
He asked, why is the performance of this approach for cases where the fluid and particle velocities are very close in magnitude?
So the difference between the fluid and particle velocity is, what we call the slip velocity or the drift velocity, need not be small, right? So the particle Reynolds number is characterized based on that velocity difference. And it turns out in these sort of cases with clustering, what you get is the particles entrain the flow, and that leads to smaller slip velocity and reduced drag, and that's sort of the origin of the clustering itself. But outside the clusters, the slip velocities are quite different, meaning we have particle Reynolds numbers upwards of 50. So that's based on the slip velocity and then the particle diameter and the viscosity. We're specifically looking at cases where we have finite slip velocity. Otherwise, we wouldn't have turbulent kinetic energy produced by the particles. Now, in this community, in the incompressible flow world, particle Reynolds number 50 is usually considered quite high. But I don't know if your background is more in compressible flows, or think about ballistics, those particle Reynolds numbers go up to, most drag laws go up to 200,000, and that's a very different type of regime here.
All right. Okay, thank you, Jesse. Another question from Freddy. Will you be considering Magnus forces as the particle rotates? May you comment on the collision model in
Yeah. I thought I would be I originally had too many slides. So I removed slides and talked really fast and ended much earlier than I thought. But the collision model, we use a classic soft sphere collision model. The idea is particles are treated as a mass spring damper. So our simulation time step is restricted such that particles can't move more than 1/10 their diameter per time step. And so this is essentially, we can account for rotation and inelastic collisions. And the reason we use a soft sphere model is because in these types of flows, you can have sustained contact with multiple particles. And so a hard sphere type of approach might have a hard time with that. But the idea of these lift forces is a good one. We find in general, in terms of lift, you have Safman lift. So you have gradients in the fluid that can induce lift. And then you have Magnus lift, meaning the particle is spinning, and that can induce lift. Usually for these gas-solid flows, high density ratio, those are usually not very important. And so a long time ago, I looked at Magnus lift, and it was really playing almost no role here. But with that said, we have a collaboration with Filippo Coletti, who's doing simulations of riser flows in ducts, so wall-bounded flows in this sort of regime of like near 1% concentration, and really nice particle tracking, velocimetry, and so forth. And we're finding that when you have wall-bounded flow, lift might be more important. And so we're sort of doing a sensitivity analysis now on those various forces. But I don't think Magnus is playing much of a role here. And to be clear, our particle rotation is only due to collisions. So when particles collide, there's a tangential component that can induce rotation. We don't have any fluid coupling for the torque. But again, the density ratio is usually at 2,000, so it should be quite small. So I don't think Magnus effect is going to be very large for these flows.
Okay, thank you. Thank you very much, Jesse. I do not see any other questions from chat room. So I don't know. That doesn't mean we don't.
Yeah, like I said, I'm happy to take any questions offline.
Yeah.
And I do want to mention my postdoc Aaron is he's currently on the job market, and he's restricting himself to the California region. So and he's fantastic. He's absolutely fantastic. So I just wanted to mention that before I sign off.
All right, sounds good. Well, let's thank our speaker Jesse today for the wonderful talk. I mean, the simulations you're dealing with is really complicated, and I think you are doing wonderful research right now. Okay, thank you so much. And with that, we're gonna end our DDPS seminar today, and next DDPS seminar is going to be next week. So please stay tuned, and yes, thank you. Thank you, everyone. Thank you, Jesse.
Thanks again.